You must have noticed that there has been a sudden revolution in mobile phone and laptop chargers in recent years. In the past, the original chargers included with our devices were big, bulky, and got terribly hot after just a little use. But now, if we buy any third-party GaN charger, it is only half the size yet delivers several times the power. More importantly, it hardly generates any heat at all. This makes many people curious. What exactly is this black technology known as GaN or gallium nitride? Many people intuitively think, is GaN a super heat dissipating material that is more powerful and efficient than the copper we know? Is copper's dominance in the world of heat dissipation about to be ended by GaN? Today, let's ask the most direct question, between GaN and copper, who is actually better at heat dissipation? But what if I told you that this question was wrong from the very beginning? The reason GaN doesn't get hot isn't because it's good at dissipating heat, but because it doesn't generate heat in the first place. Its real enemy is the traditional material we've used for half a century, silicon. Today, let's uncover the real secret behind why GaN chargers don't get hot. To understand why GaN is so powerful, you must first recognize its true enemy, traditional silicon. 99% of the electronics in your hand right now, from computer CPUs to your inverter air conditioners, are controlled by silicon chips. In a charger, silicon plays the role of a switch. Professionally, we call it a MOSFET. Its job is to switch the alternating current from the socket into the direct current your phone needs at high speed. But here is the problem. Silicon is naturally quite lazy because its physical characteristic, called the band gap, is relatively narrow. This causes its switching action to be very slow. You can imagine it as a rusty faucet that doesn't close tightly. When you turn it on and off quickly, some water always leaks out the moment you switch it. In the electronic world, this leaked energy turns directly into waste heat, which we call switching loss. This is the root cause of why your old chargers were big and hot. And because silicon switching loss is so high, engineers had no choice. They had to stuff huge chunks of copper or aluminum heat sinks into the charger to passively conduct this waste heat away. That's not all. Another disadvantage of silicon is that because it switches slowly, its operating frequency cannot be increased. It can roughly only work within the range of tens of thousands of hertz. According to the laws of physics, lower frequencies require larger passive components. If you take apart an old charger, that large, heavy copper coil inside is the transformer. Those large capacitors next to it are also there to accommodate low-frequency operation. So you see, the traditional silicon charger is basically a double disaster. First, it generates heat frantically, requiring copper heat sinks. Second, it works at a low frequency, requiring copper coil transformers. Copper was never the enemy. Rather, it was the crutch that silicon, the heavy heat generator, relied upon. So, how does GaN solve all of this? Gallium nitride is a wide bandgap material. You don't need to understand deep physics, just remember this analogy. If silicon is a narrow dirt road full of resistance, then GaN is an 8-lane superhighway. Electrons run on this highway with almost no resistance, bringing two revolutionary advantages. The first advantage is extreme energy efficiency, meaning it doesn't generate heat from the source. GaN switches at an incredible speed, hundreds of times faster than traditional silicon. Using the faucet analogy again, if silicon is that rusty old faucet, then GaN is a brand new nano-grade precision ball valve. It can open and close in an instant, with almost not a single drop of water leaking out. This means GaN switching loss is minimized. Let's look at the data. The energy efficiency of traditional silicon chargers is about 90%, while GaN can easily achieve 95% or even higher. You might say, it's only a 5% difference, right? You are wrong. For engineers, this 5% efficiency improvement represents a reduction of more than 50% in wasted heat. Since GaN itself doesn't generate much heat, it naturally no longer needs those big, bulky copper heat sinks. The second advantage is ultra-high frequency, which means extreme compactness. Because GaN switches fast, engineers can increase the charger's operating frequency from hundreds of kilohertz to the megahertz ms level in one go. Remember, physics says lower frequency needs a larger transformer. Conversely, higher frequency allows us to use smaller, lighter transformers and capacitors. The bulky transformer wound with copper wire that used to take up half the charger's volume can now be shrunk to the size of your fingernail. This is the real secret to why GaN chargers can reduce volume by 50% and reduce weight. It didn't just remove the heat sink, it shrank the transformer and capacitors, which took up the most space. So, let's go back to the original question, GaN vs. copper, who is better at heat dissipation? The answer is, this is not a fair fight at all. GaN is not a material that conducts heat better than copper. It is a switching material that is more efficient than silicon. Copper's role is passive heat dissipation, while GaN's role is to actively reduce heat generation. By completely defeating silicon inefficiency, GaN makes the bulky tools of copper heat sinks and coils no longer necessary. This isn't just a revolution for chargers. This GaN vs. silicon war is being fought on all fronts. In the future, data centers can save millions of watts of electricity, and EV inverters can be lighter and more efficient, directly increasing range. Solar inverters will also be able to convert energy with less loss. GaN is not only changing your charger, it is changing the future of our entire power grid. Did you misunderstand the principle of GaN before? Welcome to share your thoughts in the comments below. If you want to know more about the duel between new and old technologies, please subscribe to my channel.